Just going to zoom in on this little graphic here about how a hyperbola is created from a cone. It actually takes two cones to make a hyperbola. If you stack them point to point and then take a perpendicular slice right down the side, you get a U shape and then another U shape, and that's how you get a hyperbola. Just looking at the technical definition of a hyperbola real quick. Technical definition is the set of all points where the difference in the distance from two fixed points, those two fixed points again are called the foci. The difference in the two fixed points is constant. And that's different than the definition for an ellipse. Ellipse was the set of all points where the sum in the distance from two fixed points is constant. So hyperbola has difference in the distance. Just like an ellipse, hyperbolas can face two different directions. We can have a horizontal hyperbola where you have a left-facing and a right-facing branch, or you can have a vertical hyperbola where you have a up and down-facing branch. And you actually figure out which way it faces slightly differently than how we did for an ellipse. For an ellipse, it was just based on the larger of the two denominators determined which way it faces. But for hyperbolas, for a horizontal hyperbola, if x is the positive term, that's how you can tell it faces horizontal. So if we look down here in its little equation, there's always going to be one positive term and one negative term on a hyperbola. For a horizontal facing one, x will be the positive one, and then y will be the one behind the minus sign, making it the negative term. So if x is the positive term, we can tell it faces horizontally. And then opposite of that, a vertical hyperbola, y is going to be the positive term. So there we can see it up front. Y is the positive term, and then you have a minus sign, and then your x term, making x the negative term. Okay. Let's see. Hyperbolas also have asymptotes, technically like rational functions. Technically a rational function was a hyperbola. And they have asymptotes on them. We also use our a and b numbers similar to how we did them on an ellipse, except once we have our a and b, we don't get to draw the shape automatically. Once you have a and b, you're just going to use those a and b to draw the little center box. The center box helps you find your asymptotes, and then the asymptotes help you draw your actual equation. We can look and see inside each of the little cups of the hyperbola, we have our two little focuses, our foci. You can see them inside the cup here, inside the cup here. Similar for a vertical one, you can see them inside the little cups of the hyperbola, not parabola. To find C, C is similar to how we did C for an ellipse, except for an ellipse we had to subtract a and b. For a hyperbola, we're going to be adding a and b. I'm going to pull out that little green chart I gave y'all at the beginning. You can see for an ellipse, the c squared, you subtracted your a squared and b squared. But for a hyperbola, you add your a squared and b squared. How I remember that in my brain is for an ellipse, there's a plus sign in the equation. So you subtract to find c. And then it's opposite for hyperbolas. For hyperbolas, there's a minus sign in the equation, so you add to find c. That's how I keep it straight in my brain. Let's try one. All right, looking at our first one here, I can see the minus sign is telling me it is a hyperbola. My h and k, actually let's start with just horizontal vertical. Okay, remember horizontal or vertical is based on which term is the positive term. So I can see my x term is the positive, my y term is the negative. So if x is the positive, it faces horizontally, yes. So you'll have a left-facing branch and a right-facing branch. Okay. My HK center, remember H is always paired with the X, K is paired with the Y, but if I don't see those numbers, what are they? 0. So my H is 0, my K is 0, which means my center is at 0, 0. Okay, I'm going to go over to my graph and graph that center at 0, 0. Okay, so we're going to use the denominators in a similar way that we did them for our ellipses. We're still using their square roots, we're still counting in different directions, but it doesn't help us just draw the shape. So starting with the denominator under the x term, it's a 16, so I'm going to use its square root, which is 4. So I'm going to count 4 in the x direction from the center. 4 in the x direction from the center means 4 left and 4 right. 4 left and 4 right, and plot little points. Okay. The number underneath the y term is a 49. So we'll count 7 in the y direction from the center. So from the center, we'll go 7 up and down. Okay, and then instead of drawing our shape like we did for an ellipse, what we're going to do with these is we're going to connect them with a rectangular box. Okay? I usually draw it with dotted lines because it's not technically the hyperbola, but it helps you draw your hyperbola. So connecting them with a rectangular box. Now, if you have some sort of ID badge, human geo note card, ruler, pad of Post-it, some sort of sharp, nice edge, we're going to draw our asymptotes in. The asymptotes actually go down the diagonal of this box. So we'll have one that goes from the top right to bottom left and passes through the center. You'll have another that goes from the top left to bottom right and passes through the center. So just try your best to get those two drawn in. Again, draw them with dotted lines because they're not your actual hyperbola, but they just help you draw your hyperbola. There's one. There's two. Alright, so just writing in all of the information now. We usually don't write the co-vertices for a hyperbola. We only write the vertices. And for a horizontal facing hyperbola, the vertices are going to be the ones that are in that horizontal line here. So this one's going to be a vertex and this one's going to be a vertex. So again, we don't have to write the co-vertices for a hyperbola, just the two vertices. So I can see one of them is at -4, 0. And the other is at 4, 0. My two foci, I haven't actually drawn them in yet, so I'm going to start by finding that focal length, which is my C. So again, our formula is c squared equals a squared plus b squared, which basically adds my two denominators, 16 plus 49. So c squared equals 65. So that means c equals the square root of 65, which I don't think that simplifies, because 65 is just 13 times 5, and both of those are prime. We do need some sort of decimal approximation so that we can graph it, though. What is that about? 8 point, yeah, just slightly above 8. Your two foci, again, are going to be inside the cup of the hyperbola. So if these my two vertices, my foci should be a little bit further. So they're both going to be on this horizontal axis, c units from the center. C units from the center. So 8.1-ish right and 8.1-ish left from the center. 1, 2, 3, 4, 5, 6, 7, 8.1. 1, 2, 3, 4, 5, 6, 7, 8.1. When I write those, though, I do want to write their exact values. I don't want to write 8.1 and -8.1. I want to say one of them is square root of 65 to the right, and then it did not go up at all, so square root of 65, 0. And the other one, we just went left square root of 65, so negative square root of 65, 0. For the asymptotes, we're going to write their linear equations, which for these, because they go through the origin, it's not super hard to write the linear equations. We can do them pretty easily in slope-intercept form. If we think about their slope, thinking about this one first, to find its slope, we have those numbers already. That's basically how much we counted for our box numbers. What would be our rise over run to get to that top right corner? 7 over 4. Yeah, because we went up 7 and right 4. For the other one, it would just be the opposite. It should be negative 7/4. So we went up 7 and left 4. So we're going to write y equals, there's two different slopes. One of them was positive 7/4, the other one was negative 7/4. And then what's the y-intercept for both of them? 0. So we don't even need to write. And then last thing we need to do is actually draw in the branches of our hyperbola. All we've done so far is find all the stuff that's part of it. So my last step is to actually draw the branch. There's two branches. There's two branches. One of them is going to start at this vertex on the left and going to curve around based on the two asymptotes. And then the other one's going to start at the vertex on the right and curve around based on the two asymptotes. I think these are easier to draw. They're very complicated building up to it, but I don't have to worry about it being perfectly egg-shaped or circle-shaped. Alright, let's look at the one on the back side. It's not quite in standard form. It still has one more thing it needs to do to put it in standard form. What is that one more thing? Divide by 441, because we need it equal to 1 on that right side. I'm pretty sure 9 goes into 441. Do we know how many times? 49 times. So then that means 9 goes into 441 9 times. So if I clean that up, I'm going to have y plus 3 squared over 49 minus x plus 5 squared over 9 equals 1. Now determining which way it faces, remember it's based on which term is the positive term. On this one, y is the positive term, x is the negative term. So if y is positive, it's going to face vertically. Good job. Vertically means you're going to have one piece of the hyperbola that faces up and one piece that faces down. Now be careful with your HK center. The center is always at HK, but the H is in the wrong place that it normally is. We usually see it up front. We just assume it's the front one, but H is actually always paired with X, and K is always paired with Y, no matter where they're in. So when we write down our H and K, we just need to make sure we write them with opposite signs, which means my center will be at -5, -3. Very good. Okay, I'm going to go ahead and plot the center at -5, -3. There it is. And we're going to find points that are on the center box now by using these two denominators. So I'm going to use the square root of 49, which is a 7, and we'll count 7 in the y direction from the center. So 7 up and 7 down from the center. Okay. And then underneath the x term is a 9, so we'll use its square root, which is a 3, and we'll count 3 in the x direction from the center. So from the center, 3 left and 3 right. We'll draw our little rectangle through those now. Okay, once we have our rectangle drawn, then we can draw in the asymptotes, which are going to go down the diagonals of that rectangular box. That is 1. wish my ruler was see-through. It'd be easier to line it up with things. There's the second one. Okay, thinking about which of those 4 points are the vertices. If this faces vertical and we have one branch facing up and one branch facing down, are the left-right points going to be the vertices or the top-bottom points? The top-bottom, yeah. So this top one's a vertex, this bottom one's a vertex, because ours is going to face up and down. So let's see, one of them is at -5, 1, 2, 3, 4. And the other is at -5, I think that's -10 all the way down at the bottom. To find the foci, we need to find C first, which is our focal length. That's going to be C squared equals your A squared plus your B squared, which is just adding your two denominators, 49 and 9. So C squared equals 58, which means C equals the square root of 58. And I don't think that simplifies because 2 and 29 are the only factors, and both of those are prime. But we do need an approximation so we can graph it. 7.6 sounds great. So since this one faces vertically, your foci are going to be on that vertical axis lined up with the center and the vertices. 7.6-ish units from the center. So from the center, we'll count 7.6 up and 7.6 down, and that's where our two foci are going to be. When we write their ordered pairs, though, we need to make sure we write their exact. We don't want to say 7.6. Both of them have the same x value. Basically, both of them have -5 as their x value. -5. But their y value is what's going to change. So we had one similar to this when we graphed the ellipse the other day. So we started at this y of -3, and we went up square root of 58. So that would be -3 plus root 58. And then again, we started at this y of -3 and we went down square root of 58. So that would be -3 minus root 58. And then for the asymptotes, if you look, it's actually not super hard. I mean, it's not super easy to write these in slope-intercept form. Do y'all know why it's not easy to write these in slope-intercept form? It's not at the center. It's not at the center. It's hard to see where the y-intercepts are. So what we're going to do instead is we're going to use another form of a linear function. It's called point slope form. I don't know if you remember this from Algebra 1, but point slope form is y minus y1 equals your slope, parentheses x minus x1. And for the x1 or y1, you can just use any point that the lines go through. And they actually both go through one very similar point. What is that point? The center. They both go through the center, which is at -5, -3. So that's what you're going to use for your x1 and your y1. This is my x1. This is my y1. So when we write y minus this y1, y minus -3 is going to be y plus 3. The slope is just positive and negative, and then we can just count the rise over run to get from the center to the diagonal corner. What would that rise over run be? 7/3. So positive and negative 7/3. And then we'll have x minus the x of the center. So x minus this -5 would be x plus 5. And you do not have to distribute them out. It's not needed. If you want to, if you just like distributing and you like fractions, you can, but you don't have to. And what's the last thing we want to do after we have everything written? Yeah, draw the actual branches of your hyperbola. It's going to start at the vertex and kind of curve around based on the asymptotes. The one on the bottom is not going to quite fit, but I'm going to draw as much of it as I can. It's going to start at the vertex and curve around. Yes. I will actually get mad if you don't leave it like that, because I usually have my answer key written like this, and if you write it differently, I'm going to have to be like, dang it, is mine the same as yours? So, yeah. All right, next one. We're going to remind ourselves how to complete the square. This is what we learned last week. What's my first step for completing the square? Group similar terms. Put the x's together, put the y's together. 16x squared. I'll move my negative 96x over there. And then remember to move your constant to the other side of the equation. And that creates those two groups. Before you add your completing the square number, what do you need to remember to do? Yes, take out that leading coefficient. For the first one, it would be a 16, which should leave me with x squared minus 6x. And then I'm going to leave the blank to complete the square. For the second one, when we factor out the leading coefficient, we don't just want to factor out 9, we want to factor out negative 9, which should leave me with y squared minus 4y plus blank. Okay, and now that we have the leading coefficient factored out, we can find our completing the square number. Remember, we take the b, we divide it by 2, and we square it. So for the first one, that would be negative 3 squared, which is 9. But is 9 what I want to add to the right? No, what do we add to the right? 16 times 9, which is 144. Okay. For the second one, I'll take its b, which is negative 4. We'll divide it by 2 and square it, which is negative 2 squared, which is 4. But I don't want to add 4 to the other side. I want to add negative 9 times 4 to the other side, which is negative 36. And that should create both of these parentheses are now perfect squares, which means we can write them as just that one factor squared. What is the one factor for the first group of x's? X minus 3, good job. And then the second group, the y's, y minus 2, very good. And then the right hand side is going to simplify to just 144 because the 36's are going to cancel. And then our last thing, we want to make sure we have a 1 on the right hand side, so we want to divide everything by 144. And then simplify. That first one, 144 is divisible by 16. How many times? 9. So that means 9 goes into 144 16 times. Don't forget to bring down your minus in the middle. Don't lose it. All right. Beautiful little standard form. I can see the x is the first term that's the positive term, which means it's going to face which way? Horizontally. So you will have a left branch and a right branch. My HK center, remember H is always paired with the X, K is paired with the Y. So my HK center will be at 3, 2. Okay, I'm going to go over to the right and plot that center at 3, 2. Bless you. After we do the center, remember we're going to use those denominators to help us draw the center box. I'm going to use the square root of 9 in the x direction, so from the center, 3 left and 3 right. And then I'll use the square root of the 16 in the y direction, so from the center that means 4 up and 4 down. And then we'll draw our rectangle around those 4. That's a great question. Once you have your rectangle drawn, we're going to draw our asymptotes down the diagonals and through the center. Okay, if this is a horizontal facing hyperbola, facing horizontal, out of those 4 points, which ones will be our vertices then? The left, right, or the up, down? The left, right. These two are the vertices, right? Again, for hyperbolas, you don't have to write the co-vertices. They're not usually needed. So let's see. One vertex is going to be at 0, 2. The other one is at 6, 2. To find your foci, we'll need to first find our C, our focal length, which is our a squared plus our b squared, which, hallelujah, is a whole number. Focal length is 5, which means our two foci are going to be on the main axis, which is technically the horizontal axis for a horizontal hyperbola, 5 units from the center. So 5 left and 5 right. Which, again, those are integers, which would be nice and easy to write. And the first one's at -2, 2. And this one is at 8, 2. The two asymptotes, again, you can use point slope form. Now you know about it. You can use slope intercept form if you want to. If you use point slope form, remember they both go through the center point, so that's the one you use as your x1, y1. So I'm going to use 3, 2 as my x1, y1. So I'll have y minus the y1 equals, and then we can do plus and minus of the same slope. To get from the center to that top right corner, what is the rise over run slope? 4 over 3. And then we'll have x minus the x of that center point. And again, you don't have to distribute it out unless you just really like fractions and distributing. And what's the last thing we want to do? Actually graph it. Yeah, we've done everything but actually graph the hyperbola. So since it's a horizontal facing one, it's going to start at that left vertex and curve around, following the asymptotes. And then the right one, same thing, curve around, following the asymptotes. And then the last one, we're actually going to go backwards. I actually think it's probably the easiest one. No, the graph's helpful though, to kind of visualize which way it faces, the center, etc. So again, on the last one, you don't have to graph, but it's good if you're a visual learner. First thing we're told is the two vertices. I have one at -5, 9 and one at -5, -9. So I'm going to graph those. One at -5, 9 and one at -5, -9. And then we're told the foci, one's at -5, 15, and one is at -5, -15. Just based on the graph, you can tell which way this is going to face. Is this going to be a horizontal hyperbola or a vertical one? It's going to be vertical. Faces vertical. What do you know about it if it faces vertical? Which term is the positive term? Y is positive, yep. So you can kind of start setting it up. You know that Y is going to be the first term. That's the positive one. I know there's going to be a minus in the middle. I know there's going to be some fractions. I know it's equal to 1. The second thing you can probably figure out is where the center is, because the center should be the midway point between the two vertices. What is my center going to be at? Ordered pair, the whole ordered pair. -5, 0. There's my center. And remember, that is your HK. Does the H or the K go with the Y? The K. So do I have to write plus 0? No. For the X, though, what do I want to write? Plus 5. What else are those two numerators missing? The tops are missing what? Square, right. For the first one, you can just write y squared, but for the second one, put in parentheses and then square. Okay, now we can figure out what number was under y pretty quick because we can see how much we counted in the y direction. From the center to the vertex was how many units? 9. So I know my a is 9, which means underneath y squared should be 81. Now we can't necessarily see how much we counted in the x direction. So what we're going to have to do for that is work backwards with our c amount. Because I can see my focal length here. My focal length is how many units? 15. So we're going to use the fact that we know that c squared equals a squared plus b squared. And I'm going to plug it in and solve for my missing one. So c squared would be 15 squared, which is 225. Your a squared is 81. And you're solving for your b squared, which would be 144. Now, underneath the x term, do I need to write 144 or do I need to write 12? You need to write 144, right. And that's it. We found our two denominators. We found our HK. Perfect.